Hello. This is a presentation by Martyr Inc. about novel technique of high-speed magnetic recording. My name is Boris Tankilovich. I will be presenting this new invention for us. First of all, let's talk a little bit about conventional memory cell, MRAM. Magnetic resistive random access memory is a type of non-volatile memory which stores data in magnetic domains, as opposed to the method of using electrical storage. Currently, memory technologies used, such as flash, RAM, and DRAM, have practical advantages, so RAM still doesn't have a big role in the market. Unlike conventional RAM chip technologies, data in MRAM is not stored as electric charge or current flows, but by magnetic storage elements. The elements are formed from two ferromagnetic plates, each of which can hold the magnetization, separated by a thin insulating layer. One of the two plates is a permanent magnet set to a particular polarity. The other plate's magnetization can be changed to match that of external field to store memory. This configuration is known as magnetic tunnel junction and is a simple structure for an MRAM bit. Memory device is built from a grid of such cells. The conventional interpretation of RAM is based on magnetic tunnel junction or spin wolf. First of all, let's talk a little bit about magnetic tunnel junction. It is based on the magnetoresistive effect. Magnetic tunnel junction consists of two ferromagnets separated by thin insulator, and recording and writing is based on magnetoresistive effect, which means that if insulating layer is thin enough, typically a few nanometers, it becomes a tunnel junction. So basically, electrons can tunnel from one ferromagnet to the other. This is a pure quantum mechanical effect. This process is forbidden in classical physics. So tunnel magnetic resistance is a strictly quantum mechanical phenomenon. Magnetic tunnel junction are manufactured in thin film technology. On an industrial scale, the film deposition is done by magnetron sputter deposition. On a laboratory scale, molecular beam epitaxy used in most cases. The junction are prepared by photolithography. This is a figure that illustrates general structure of magnetic tunnel junction. It consists of two ferromagnets separated by thin insulator that becomes magnetic tunnel junction if the thickness is small enough so that electrons can tunnel. And it also has contacts in order to apply external electric field. Next slide shows simplified structure of empty THz-based MRAM cell. So MRAM cell has to have two states, 0 and 1, in order to be able to record or write information. So one of the states is represented by two magnetic layers, free layer and pin layer, magnetically oriented in one direction and parallel orientation. And the other state is represented by magnetic free layer and magnetic pin layer that oriented in antiparallel direction. So the rest of the structure is used in order to apply electric field or magnetic field to read or write information. Reading from MRAM cell is accomplished by using this magnetoresistive effect that we discussed a little bit. So particular cell is typically selected by powering associated transistor that switches current from a supply line through the cell to ground. So this is accessing the particular cell. Because of ferromagnetic resistance, electrical resistance of the cell changes with the relative orientation of optimization in the two plates. More particular, when orientations are directed parallel, the resistance is low resistance state, usually considered to be 1. When the alignment, when it is anti-parallel, resistance will be higher, and it usually signs the meaning 0, bit 0, state 0. There are two states, 0 and 1. One is parallel, another is anti-parallel. So by measuring the resulting current, because the resistance is different, we can read either 0 or 1, depending on the current that we read. Now, how conventional recording or writing is done into MRAM cell? Data can be written using a variety of means. In the simplest classic design, each cell lies between a pair of right lines, arranged at right angles to each other and parallel to the cell, one above and one below the cell. When current is passed through them and used magnetic field is created at the junction, which the writable plate picks up. This pattern of operation is similar to magnetic core memory, a system commonly used in the 60s. This approach requires a fairly substantial current to generate the field, however, which makes it less interesting for low power users, which is one of the MRAM primary advantages. There's another problem. So there comes a time when the induced field overlaps adjacent cells of a small area, leading potential false writes. For this problem, the half select or write disturb problem appears to set a fairly large minimal size for this type of cell, which creates too hidden because we have to still apply substantial current to the small area. There are two basic means to do recording. One is conventional longitudinal recording, another perpendicular recording. The MRAM cell, traditional MRAM cell, can be used for longitudinal recording, and a perpendicular recording can be used if we use not standard MRAM cell, but STT MRAM, which stands for the another kind of memory we can talk about in a second. So in longitudinal recording, magnetic head writes by changing magnetic field that is parallel to the surface of magnetic resistive random access memory MRAM. The change of magnetic field causes change of the orientation of magnetic beam of the recording layer. This process is based on the tunable magnetic resistance effect. Its advantages in non-volatility, low power usage, good shock robustness, and first generation was produced by Spin a long time ago, almost 10 years ago. In order to utilize perpendicular recording, we need to use spin transfer torque effect as the basis for the magnetic cell. Spin transfer torque effect is the effect in which orientation of magnetic layer in a magnetic junction can be modified by using a spin polarized current. Charge carriers such as electrons have a property known as spin, which is a small quantity of angular momentum intrinsic to the carrier. Electric current is generally unpolarized, so it has approximately 50-50 spin up and spin down. Spin polarized current is a current in which electrons with one polarization are in excess of the electrons with other polarization, spin orientation. In this case, we have a current that has some spin torque, and by sending the regular current through the thick magnetic layer, you can generate spin polarized current, and applying this polarized current to the second thinner magnetic layer, we can transfer angular momentum from the current to the layer, changing its orientation. So as was mentioned before, perpendicular recording can be used in the random access memory devices that is based on the spin transfer torque effect. So as was said, the spin transfer torque can be used to flip the amortization in the free layer, and in such a way we can change the position, the representation of the bit from 1 to 0, 0 to 1. The spin transfer torque RAM element has advantages over the regular magnetic RAM because it requires low current in order to do recording or reading of the information. Because we don't use external magnetic field, use magnetic field of the current itself. So this kind of memory attracted substantial attention from many leading companies like Crocus, IBM. But the result is not here yet. So it hasn't become the dominant memory yet. So let's take a closer look at the spin wall magnetic tunnel junction. As we see, the two resistance states, high resistance, and high resistance, low resistance, depending on whether free layer or fixed layer are oriented in the anti-parallel orientation or parallel orientation. So in the magnetic wave, the spacer is metallic, as opposed to magnetic junction when it is an insulator. As we discussed before, usually it becomes tunable magnetic junction. So let's take a closer look at just spin wave that has metal, and this metal can be used in order to change orientation, magnetic orientation between pinned and pinned layer. Let's talk about that. And this change orientation is based on the RKKY effect. RKKY interaction is a Ruderman-Kittel-Kasuya-Yosida interaction, and it is well studied and experimentally proved. For many spacers, we'll just use Ruthenian spacer. It is the mostly used spacer for these purposes. As it is seen on this diagram, the Ruthenian spacer, if it has thickness about 8 angstrom, can implement antiferromagnetic interaction between free and reference layers. But if we can change the thickness, increase it up to 12-13 angstrom, it can provide ferromagnetic interaction. So let's go back a little bit. So the issue is, can we change the effectively thickness of the ruthenium layer between spin and pinion layer so that it will change sign of the interaction from antiferromagnetic, if the spacer is only 8 angstrom, to ferromagnetic interaction, when the spacer is a bit thickness a bit higher, like 12 or 13 angstrom. What is interesting is that actually it can be done by applying terahertz radiation, as was predicted and numerically confirmed in this paper, Control of the solar interplane exchange interaction with terahertz radiation, published in 2017. And we can implement this technique by using invented by bacteria THz Magnon Laser to manipulate RKKY-based spacer and provide very fast recording capability, because we can generate terahertz between basically from 5 to 30 terahertz. And based on this paper, the effect can take place if the terahertz radiation applied between 10 and 100 terahertz. So the radiation that we can apply from 10 to say 30 is sufficient in order to achieve this effect. As you see, there is a color coding on this diagram, goes from dark blue, which correspond to antiferromagnetic coupling through RKKY interaction, to the red ferromagnetic coupling. So it can be done by applying terahertz radiation. In our case, between 10 and 30 terahertz, that we can achieve. Let me say a couple of words why actually it is happening. Basically, by applying external radiation, we effectively change the time of flight of electron in the tonal junction, in the ruthenium, in the spacer. Indeed, the time that is necessary to propagate through the spacer depends on the velocity of electron and the thickness of the spacer. Velocity of the electrons at Fermi level usually 10 × 6 meters per second, and the spacer usually, let's say, we are talking about 10 angstrom, let it be 1 nanometer. So if we divide 1 nanometer by velocity 10 × 8, we'll get 10 × 6, we'll get like 10 × 15 for the frequency. However, that's not the right application, because in reality, we have to apply this reasoning not to the time of flight directly, but for the strength of the interaction, because we are talking about changing the sign of the interaction. RKKY interaction decreases with the distance as r minus power is -3, 5 power decreases inversely proportional to a third power of distance. So this third power distance gives us additionally decreases this frequency from 10 × 15 to 10 × 12. That brings us to the terahertz frequency region. I'll be happy to discuss it if there are questions in more details. So now about our THz Magnon Laser that actually can provide such capability. Actually, the only device on the market that can be manufactured, fabricated with have a proof of principle. We are working now on the fabrication of this device using sputtering technology. So far it was used by using molecular MBE technology, molecular beam evaporation for the prototype, but now we are extending to the sputtering technology to make it, to be able to manufacture it at commercial, industrial scale. And the process is used to manufacture THz Magnon Laser as basically absolutely very similar to the processes that are used for the manufacture of the magnetic junction. So existing fabrication lines can be easily adjusted to add the THz Magnon Laser as a writing head and to implement this high speed of magnetic recording. THz Magnon Laser was invented by Magtera, and we have numerous patents to this effect. It's well protected in IP space. So let's say again, so what we are going to do, we are going to use the THz Magnon Laser as an optical writing head for longitudinal recording by changing the orientation of a signal memory cell on the recording layer. The change in orientation is achieved by changing the exchange interaction sign from ferromagnetic to antiferromagnetic and vice versa of the RKKY spacer. Usually it is ruthenium spacer, but other metals can be used like copper. For copper, RKKY interaction is a bit weaker than for ruthenium, and antiferromagnetic kind of coupling is achieved at 7 angstrom instead of 8. But basically the effect is the same. Ruthenium spacer is very good because the RKKY interaction survives really high temperature and will be stable at room temperature applications. Now, so let's look at the new way of recording that we offer, that we invented. This is the device that is used in optical magnetic writing, optical terahertz writing head. So basically what it means that we don't use electrical current here. The electrical current here used only to generate terahertz radiation. So heating of the writing layer will be negligible, which means that we can eliminate almost heating problem. For the terahertz writing head, we can use some heating. We can use cooling systems that are applied only to the recording head, not to the writing space itself. So it means that we can apply this optical recording head to very small areas without excessive heating. So the device is very simple. Basically, we use a memory cell that includes a spin valve that has 2 layers, reference layer and free layer, separated by ruthenium spacer. And we irradiate this cell in such a way that we can affect ruthenium spacer. And by applying terahertz radiation, like let's say 10 terahertz, we can achieve change of coupling from ferromagnetic to antiferromagnetic and vice versa. Now we can apply the writing signal as a bias voltage to the THz Magnon Laser at very high speed. much higher than conventional recording systems. Like we can apply writing signal at this frequency of 100 gigahertz, even 1 terahertz, which means that we can do recording hundreds of thousands times faster than a regular recording systems without really hitting effects. This new way of recording would be very important in the artificial intelligence applications, because artificial intelligence analyzes extremely large amount of data, and in order to analyze data, you need first to record it. This method of recording can offer such opportunity. So again, our device has standard memory that has Wolf with RKKY spacer, and we can change the memory bit from 1 to 0, 0, 1, just affecting recording or writing information by eliminating memory cell using THz Magnon Laser. Now, THz Magnon Laser, as was said before, is a device that can be simply fabricated using the same technology that they use for fabrication of magnetic junctions. Indeed, THz Magnon Laser has almost the same elements. It has 2 ferromagnets. We use half metal instead of regular ferromagnetic metals for our purposes. We use the same tunable junction, and then we have pinion layer and contact beds the same way as used in the magnetic junction. In our case, we don't need to change orientation between upper layer and bottom layer, because we need to keep antiparallel orientation between top half metal and bottom half metal to achieve functioning of magnetic Magnon laser. That concludes my presentation.